Hello, my mouse cursor is now disabled, which means that you should hopefully not be able to see it flying around in all the subsequent videos. Alright, now the question. Let fx be the natural logarithm of 1 plus x. By considering the integral of the derivative of fx, show that fx is this sum here. So it's an alternate way to express fx. First, let's start by finding the derivative. F dash of x is equal to, well, it's just 1 over 1 plus x. Now, we have like a series here, so it makes sense to consider what we know about geometric sequences. And if this isn't infinite, this means maybe it's some sort of infinite geometric series. How does that look in general? Well, in general, a geometric series, a sum to infinity of a geometric series, can be expressed as a over 1 minus r. And if we were to substitute these values in to the 1 over 1 plus x, then we end up with a is 1 and r is minus x. And if that is the case, we can reverse what we've done before. F dash of x would be equal to, well, the first term's 1, and the second term, well, it'd be minus x, and then the third term, it'd be x squared, and we're timesing by the ratio each time, and so on. So, what happens when we integrate? Well, we will have to integrate each term separately, and this will be the integral of 1 dx minus the integral of x dx plus the integral of x squared dx minus, and so on. Considering the left side and the right side, we end up with fx is equal to x minus x squared over 2, because we've added 1 to the power and we've divided by the new power. And here we've added 1 to the power, divided by the new power, and so on. And this gets us our expression that we wanted. When x is less than a, though, the modulus of x has to be less than a. And you will notice that if you put in certain values into here, the expression doesn't quite work out. Let's try f of 2. And this would end up being 2 minus 4 over 2 plus 8 over 3 minus 16 over 4 plus 32 over 5 plus... Wait, this is getting bigger. Like, this term here is much bigger than this term. And overall, this will go like up, down, up, down, up, down, it will never converge to a value. This infinite series doesn't converge. So clearly, we want it to be smaller than 2, but how small do we want it to be? Again, if we consider the fact that this is just a geometric series, we know that the radius of convergence for a geometric series is where the modulus is less than 1. So we just put a is equal to 1. Now we're asked to find an alternate expression for arctan of x and show this actually quite nice identity, that if we take 1 and minus a third and add a fifth and minus a seventh and so on, we get pi over 4. Surprisingly, this is a very nice way to calculate the digits of pi if you don't happen to have a calculator on hand. Of course, now it's pretty redundant. We're going to use the same technique as before, and that is that we want to integrate the derivative of arctan x. So we have fx is equal to arctan x. Now, this is a standard derivative in most A-level booklets. However, we're going to show that this is true anyway. Just a bit of practice. If we set y is equal to arctan of x, then we can unapply, or rather apply tan to both sides to get tan y equals x. Then we work out dx over dy, so the derivative of x with respect to y, and this is sec squared y, which is also a generally well-known differential. Then we flip the expression here. I'm going to keep sec squared down here because we can use some of the trig formulas here to end up getting what we started with. Because we don't want to keep it in terms of a sec squared of y, we want this to be in terms of x, if we can. A well-known identity is that sine squared x plus cos squared x is equal to, or is identical to 1. And if we divide by cos squared, we end up with tan squared x plus 1 is identical to sec squared x. Oh, we already know what this is. This is just 1 over tan squared y plus 1 is equal to dy over dx. And now we can replace this tan squared y with what tan y was, which is just x. We end up with this equal to 1 over 1 plus x squared. And this is our f dash x that we want. Now that we have it, we can see that again, this is a geometric series with a equals 1 and r equals minus x squared. And again, when we integrate, we want to integrate the differential of x. We end up with 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8, and so on. This ends up being 1 minus x cubed over 3 plus x5 over 5 minus x7 over 7 plus and so on. And actually the ball's getting a bit full now, so I'll just clear it so we can finish up. So we've worked out the alternate expression for arctan, and now we just need to show that this identity holds. And as you can see, I've paired it along here, and this I wonder what the value of x could be that I have to plug in. Yes, it's x equals 1. And arctan of 1 is of course pi over 4. It's a nice interesting result, I'd say.